Okay, so thank you all for coming, and thank you, Urs, for accepting the invitation. Today we have Urs Schreiber telling us about super exceptional geometry for 11-dimensional supergravity. Please, Urs, it's a pleasure to have
Thank
you
you very
here.
much. Yeah, thank you very much for the invitation. I do appreciate it. So this, as you all know, is work we did very recently, closely related to things you're doing. And I want to motivate a little bit how we arrived at this and then state the main observation that we put recently on the archive and close with a little outlook of what we think this does for us at least. And please feel free to interrupt me if there's anything. I'll try to go through it slowly, so that we all know what's going on. I'm trying to recall some basics too. So let's see. So our starting point is the observation that there is something interesting, maybe more interesting than has previously been appreciated in just super tangent spaces and the superfluxes they carry. Let me try to explain this very briefly on just one page, and this will lead us over to our motivation for thinking of the M-algebra as having anything to do with U-duality symmetries. So I call it here the unreasonable effectiveness of supertangent spaces due to two theorems that I'm going to state in just a moment, which are partly folklore, but I think fully proven only recently. So I'll be looking just at the ordinary familiar supersymmetry algebra of an 11D, which, just to set up my notation, I'm showing here. So this is my notation for the super Poincare algebra, the full supersymmetry algebra, and I'll be focusing on its translational part, the super translation algebra in 11D, which I write in this supermanifold notation R1, 10 with 32 Majorana spinor representation being the odd directions. And in fact, I'll always be speaking about these super algebras in the dual formulation, which is standard in the supergravity literature, I think. But just to establish my notation that I'm using here, so we're calling this the Chevalley-Eilenberg algebra. It's just the usual dual notation that you all know. So, like mathematically, these are the left invariant one forms on our super-Minkowski space. Some regarded as a super group instead of just a super Lie algebra. But what it really means is just that we're looking at the differential graded commutative algebra that is generated from these psi alpha, which are in odd degrees, so the one forms in odd degree. This is our Gravitino, and the ordinary, well, the super version of the ordinary Vielbein, capital EA, which satisfy this crucial differential equations. So psi is closed and D is not closed. Its differential is that square, that vector valued square of the spinor. This is the crucial equation. This is the dual of the famous, the emblematic super bracket. This is the dual of Q, Q is a momentum. And what is of interest for what I'm trying to say here is that, simple as it may seem, just a slight generalization of the fully trivial bosonic translation algebra, there's something really deep going on already with this translational part. Namely, it carries one can form the following spin invariant and hence super invariant forms. I call it G4 and G7. So G4 and G7 is, to remind us in a moment, these will be identified as the flux densities of the C field in duality symmetric form on supergravity, but the 0 indicates that we're not yet on a curved space-time. It's just the tangent space. So this is something like the super avatar of the full flux density. So 0 means not the full thing yet. We'll complete it in a moment. And it's formed by these combinations that you've all seen before. So we do a spinor pairing of a 2-index gamma matrix contracting with 2 of these Vielbeins, and do the same thing with the 5-index gamma matrix and 5 of these Vielbein forms. So these are just elements that you can form in this Cartan algebra. They're fully invariant, so they're supersymmetric in this sense. But the remarkable thing is they satisfy this equation just in this algebra here, in this DG algebra. G4 is closed, and the differential of G7 is half the square of G4. So this comes down if you just apply this equation, as you all know, but let me just recall it. If you just apply this equation here, just hit these expressions with this equation, there appears there appear two quartic expressions in the fermions, and the fact that they come out, the first one is 0 and the second one is this form, is part of the quartic. It's the main quartic Fierce identities in this dimension. So what one can do now is one can ask to globalize the situation to an 11-dimensional superspacetime, which is not necessarily just super Minkowski, but curved. So I'll allow X now to be any supermanifold that is, locally modeled of this form. So it's an 11/32-dimensional supermanifold. And for it to be a super spacetime, I have to ask it to be equipped with a suitably torsion-free metric. And in this first order formalism, so we say, okay, let there be what mathematicians would call a Cartan connection, so a co-frame field. So let there be one forms on, well, a local chart actually. So locally, let there be one forms on the supermanifold, which the first two sets look just as those that we've seen already on Minkowski spacetime, in addition to a connection form that will encode the information that we're curved now.
Sorry,
And
can I ask a question? Because
please do, yeah.
you say DG70 is 1/2 G40 squared, but if I apply D to G on the thing on the on the left, G07, I get, of course, D on psi, which is equal to 0, but DEA to DEA5, how does that turn into G4? What do you do there? Do you use fields identities or?
Yeah, that's as I try to say, this is a quartic Fierce identity, a subtle one, which holds an 11D, yes. So hitting D, hitting G7 with this, we get this expression times this square bracket. And then one has to argue, why is it that this combination of psi, with 5 indices, psi times psi1 index, psi, skew symmetrized in the remaining 4 indices is something. And yeah, that's a non-trivial statement.
So it's a Fierce identity.
That's a quartic Fierce identity, yes.
Okay, thank you.
Yeah, so I said it here, yeah, that's right. So this is a somewhat deep fact, I think, of this 11D spacetime, that it has these relations. So this was known and shown, I think, first in 1982 by Dauria and Frey in the article 11D Supergravity and its Hidden Supergroup. They tabulate the representation theory of spin 1,10 and do the the decompositions into irreps and argue that this is the case. It was later reproved by other authors, and it keeps reappearing in the literature. People keep rediscovering this without citing the original literature. There's an article by Ascaraga on extended superspaces where he seems to rederive this from scratch. It's not so clear. He states it. The first identity is often called the membrane identity. The second identity is discussed less in the literature because many people do not, but this will be absolutely crucial for what I'm trying to say. Many people do not use this duality symmetric formulation. They will just say, well, G7 is the Hodge star of G4 and not further, supplied with a super incarnation. And I'll come to this in just a second, that it's actually crucially important for what I'm saying here to start with this, what is sometimes called the duality symmetric formulation, where a priori, these two things are on the same footing. Well, I'll come to this in just a moment. The Hodge duality will emerge in just a moment. So the idea now is that we, in a way, try to globalize the situation from flat space to curved space-time by using really just Cartan's original idea of moving frames, which essentially just says, well, let's suppose we have one forms on a curved manifold that locally satisfy these same relations with a connection form thrown in. And it's crucially that as an ordinary gravity, one will ask that the connection is the unique torsion-free connection. Here we ask that the connection is a super torsion-free connection. So this equation here really is, if you're kind of mathematically inclined, it's natural to bring the term here on the right, bring it over to the left. It's just part of the covariant derivative of E by the previous equation here. And in total, this just says that the intrinsic super torsion just vanishes. So it's a torsion freeness condition. And I'll call this a super space-time because it's the analog of equipping an ordinary manifold with a metric. This is kind of equipping the super manifold with a kind of first order formulation of a super metric. And then I want to do an analogous thing now for the fluxes. Yeah, please.
Sorry, I also have a question about this because if I remember correctly, if you're in higher dimensions in supergravity, the torsion also has higher gamma matrix terms like a gamma 5.
So it has when you try to incorporate higher curvature corrections, which I'm not doing here. So with this torsion, we're going to be talking in a moment about ordinary supergravity without higher curvature corrections.
No, I don't mean higher curvature corrections. Just, I mean, if you do the first order formulation of supergravity, I think you also get I mean, the torsion terms that you get, like in 11D in the Kremer-Julia-Shork paper or something like this, has this psi bar gamma 1 psi, but it also has a psi bar gamma 5 psi, if I remember correctly.
No, in
Just in the-
11D, this is the torsion constraint. It really is, yeah.
Okay.
Um,
Okay, okay, maybe I'm misremembering
yeah, no,
that.
very, very certainly, yes. This torsion constraint looks more complicated in lower dimensions with more contributions. Here it's really just that. Yeah.
Okay, I will check. Thanks.
So the idea now is to say, well, let there also be flux forms which kind of look like these avatar flux forms. So I'm going to say, let there be a G4. The superscript S means it's like the superflux. And I want to think of it as being a kind of an ordinary flux form, even though this is also a function now on, or a form on the supermanifold, plus this G40 term, which using my co-frame field, which I just introduced, I can immediately globalize the spacetime by the same formula, where now the E's are those of the curved manifold. So declare that there should be a superflux, which in general, a 4 form could have any expansion in any number of the E's and psi's, but I ask you to have just these two components. One component that just has a product of 4 of the E's here, so that its coefficient is a 4-index skew-symmetric tensor, like an ordinary 4 flux should be, plus this psi EE term that we take from the previous case. And do the same move for G7, an ordinary, well, in quotation mark, ordinary piece, which has the ordinary index structure of a 7 flux, plus this local avatar piece. And then the first statement, which is a variant of the original theorems or the original claims, maybe by Kremer and Ferrara in the 80s, and then I think Howie, and later expanded on much by Daria and Frey and what they called the rheonomic approach. They all made a claim in one form or other that supergravity, 11D supergravity, is put on shell on super spacetime by imposing this torsion constraint and some further constraints which differ from author to author. And what we observed a while back is that a particularly suggestive form of stating this is the following. It turns out that if we now just impose the duality symmetric Bianchi identities on our superfluxes just defined, where the Bianchi identities of the same form as those that we've already seen on the Minkowski spacetime, then these two conditions, or this one condition really, this super Bianchi identity, is already equivalent to the full equations of an 11-dimensional supergravity. So this implies in particular that G7, the ordinary component, is actually the Hodge dual of G4. And that implies the Einstein equation and the Gravitino equation and the full structure of 11-dimensional supergravity. So the proof of this statement is to a large extent, the proof of the implication from the left to the right is to a large extent exactly the kind of arguments that have been at least sketched in the literature before, which have become kind of folklore, even though it's really not easy to see that a full proof has been given anywhere in the literature. The converse direction, that 11-dimensional supergravity equations of motion imply this, so that there is not more than the equations of motion implied by this Bianchi identity, has not, I think, appeared before in the literature, but it's true. It's a long computation using heavy computer algebra. So this is a kind of striking statement. It says that the structure we see just on the tangent space, on the supertangent space, including the superflux SSCs, already in a sense knows everything about 11-dimensional supergravity. And it goes a bit further. We can now also bring in the M5 brane into this story. Let's consider the usual gamma matrix that kind of projects locally, tangent space-wise, onto the world volume of a 5 brane. And so that the fixed locus of this involution here, of this operation of reflecting at all the world volume directions of a Cartesian, if you will, 5-brane in this tangent space, which carves out this subspace here of this superspace where we don't just find the sub-bosonic space, but also the sub-fermionic space, which is now two of the sort of left or right, whatever, two chiral representations of the spin 1,5 group. And by some simple Clifford algebra, one sees now that the restriction of our avatar superflux, the G40 here, to this fixed locus, so what I call the pullback along phi 0, which is my name for this inclusion of my avatar, is just 0, which I want to write in this suggestive form. It's just 0, so I say, well, it's actually d of 0. This is just to, this is a triviality, of course, which I'm just stating in this way in order to amplify the pattern, that it's of the same form as here. We find a certain Bianchi identity on these super tangent spaces, which already looks like the Bianchi identity we expect to see for the actual M5 brane in a possibly curved manifold. And to bring this out, we can proceed in the same form, in the same fashion as before. Let me maybe scroll up a bit. We ask now that we have super manifolds, an immersion of a super manifold of this lower dimension, 6/2 times 8, into our given supergravity solution. And there's a way of declaring such an immersion to be 1/2 BPS by saying, one has to be careful how to do this, by saying that it is locally like sort of tangent space wise, this canonical inclusion, which comes down to saying, well, we ask that there is a super coframe on the bulk such that its pullback along phi produces a canonical super coframe on sigma. So this, what I call here the 1/2 BPS M5 immersion condition is essentially, it's a little bit stronger than what in the literature is known as the super embedding condition in the super embedding formalism for M5 branes, or generally for branes. So there's a way a natural way to globalize this. And with that globalized, as before, we also want to go ahead and say, well, let us also globalize the flux that we've seen. Well, here it was just 0, but in a sense, sort of relative to G4, we've seen that there was a super flux on this tangent space, which trivializes, which is a co-boundary for our avatar 4 flux. So let us try to globalize the situation too in the same fashion as before. So we say that there be a super flux 3 form, which consists sort of an ordinary part with the ordinary index structure, plus its super avatar, which in this case is just 0. So now we just have a form just like this. It's just a 3-index tensor. And an analogous theorem now, which is a slight variant of familiar statements in the super embedding literature, now says that imposing on this superflux the expected super Bianchi identity, that it's a co-boundary of the pullback of our super 4 flux, that is actually part of the equations of motion that is implied by the M5 brane. Sorry, I didn't say this well. This is part of, well, this follows as part of the equations of motion of the M5 brane. So again, we see that just, in quotation marks, just globalizing the situation that we see on, in this case, this relative inclusion of supertangent spaces implies everything we want to know about the dynamics of this M5 brane thing. And it's these results that motivated us. They're a form of what mathematicians would call Cartan geometry, where one says, let's consider geometries that are locally modeled on certain coset spaces. These would be called Kleinian geometries in the math literature, where these coset spaces are kind of the local model spaces. And then we demand, or we globalize them, we curve them by saying, well, let there be curved geometries that kind of tangent space-wise look like this. So this is here for the 11-dimensional Supergravity for the M5 plane. So it's these statements that motivated us to look for possibly more sort of hidden structure in supertangent spaces. And now to lead over to, this exceptional geometry that I want to get at, or an aspect, a part of it, a fragment of it, let's look a bit at T-duality in this perspective. And I hope I can bother you with the diagram of this form here. What I want to do now is I want to, in order to see how duality comes in, let's look at the analogous situation now for 10D super spacetimes. And I'm going to denote just as before. This here is my notation for the kind of canonical tangent space of 10D type 2A supergravity. So it's R1,9 slash the 16 plus 16 bar representation curve and the other handedness for the corresponding spin 1,10 group now. And on the right, I draw the same thing. It just differs by lacking this bar here for the corresponding type 2B super spacetime. And now it turns out, ignore the middle piece for a second. It turns out, again, as before, by just looking at the super invariance that one can form just on the supertangent space without even going to any curved manifolds, one finds a very rich super invariance structure, which I'm sketching here in these gray, or not sketching it, which I'm listing here in these gray boxes. So one can certainly form, as you can see, one can form all these quantities. So here's an H3, which is built very much like the G4 before. In fact, it's the dimensional reduction of the G4 before, where we kind of picked the E10 component and then removed it. So it's psi bar gamma A gamma 10, where gamma 10 is the previous one. And in the same fashion, one can form this whole list of even degree super invariants on the supertangent space. You see, of course, this notation is already meant to suggest these appear in exactly the degrees in which one expects the RR fluxes to be. And in fact, using, again, Fierce identities that hold here, one finds that these canonically defined forms, I mean, sort of intrinsic forms, right, that just exist on the superspace satisfy exactly the Bianchi identities, again, the duality symmetric ones that one expects of the RR and NS flux in type 2A supergravity. So this H3, A is closed, and the Fs are not closed, but the differential is equal to this H3 wedge, the F of degree 2 lower. An analogous situation holds for type 2B. There's one needs to use different gamma matrices here well, if all, so here all my gamma matrices, I should say, are sort of just those really from 11D. It's just the dimensional reduction. And so here these gamma A are actually the same as before for A smaller equal to smaller than 9, and it's there's some gamma 10s thrown in to get the right spin representation. Anyway, so these things also exist on the type 2B spacetime. And the remarkable, I think, thing is now that, in fact, the Hori transform, so the full T-duality on NS and RR fluxes is actually all pre-configured in some sense on these super spacetimes in the following way. Namely, both the type 2A spacetime and the type 2B spacetime, they are fibered sort of in the obvious way over the corresponding D equals 9 super spacetime, where these maps are dually, and well, they just forget the 9th direction, the 9th spatial direction, or dually the Chevalier-Eilenberg algebras here are just the inclusions that hit everything except E9. And what one can do now is that man can form, since we have these two maps now to the this common base space, one can form what is called the fiber product of these two things, which really just means take the product of this guy with this guy, but identify everything that maps to the same thing here. So this, what I call it, the doubled super space-time, is really, I think I didn't write it down on this slide. It has the same generators as type 2A and type 2B. So it has, but all of them that are not E9 are identified. So it just looks like the 9D super space-time, but then it has two generators for E9. So there's an E9 coming from here, and the tilde E9 coming from here. And both of them are generators in this double space-time. So this is the tangent space incarnation of what in the double field theory literature, the tangent and super version of what in the double field theory literature is called the double space-time for one T-duality direction. And in the language of topological T-duality, this is the correspondence space, or the tangent space to the correspondence space. And the interesting thing now is there is a further super invariant on this correspondence space, which is the super version of what in the literature is known as the Poincare 2 form. And it's just given by the wedge product. This should be capital here. This is a typo. The wedge product of the E9 coming from here and the E9 coming from here. And the interesting thing, this too satisfies some Bianchi identity, which one can just work out. Turns out this Poincare form is the cobound. It trivializes the difference of the pullbacks of H3 here and H3 here. So they're different, but when you pull them back to this double space, the difference actually trivializes in the RAM cohomology, if you will. And this is known, and using this, one can form now this transformation, which is known as the Fourier-Mukai transform, usually, which maybe we can take these flux forms here on the 2A spacetime, pull them back along this projection map to the double spacetime, then wedge them with the exponential of P2, which really just means wedge them with 1 plus P2, because this thing is evidently nilpotent. And then do the fiber integration over this map, which just really means throw away everything that contains an E9, pick the E9 components. So it turns out that this pull-push operation, which is kind of the tangent space version of what's known as the Fourier-Mukai transform, takes all these fluxes, or super avatar fluxes, into these, and conversely. So this is the exactly, the form of this is exactly what people in the topological T-duality literature figured out is the abstract, or the, how should one say, the intrinsic way of realizing the T-duality between the RR fluxes. This is sometimes called the Hori map if you do it on globally defined superfluxes. And so this is something we noticed a while back. This was 2018. But actually this generalizes. We can, in this tangent space language, it's easy to consider something that otherwise may seem a bit exotic. We can look at T-duality along all 10 space-time directions. One reason is here that since we're in the tangent space, in this construction, we're not actually doing a topological compactification. We're just, playing with these flat directions. And there's just nothing in the formalism that prevents you to do this also to the time direction. And when one does this, one finds a duality from between type 2A spacetime and its version, which I'm calling tilde A here, which is the result of applying in the above fashion T-duality to all 10 spacetime directions. So this is now fibered over the point. It would be fibered in the bosonic case, but since we're still retaining the fermions, it's actually fibered over the superpoint, that is 32 odd directions. And its double space now is the super Lie algebra that has these translation generators, 10 of them from here and 10 tilded one from here. So this is now fully doubled in the sense that every space-time direction has a T-dual. And again, one finds that there is a Poincare form on this doubled space, which is now not just as before, the product of just, E9 with one with E9 of the other, but it's the sum over all the space-time directions of the original space-time and its dual. And it again, on the double space-time, it trivializes the difference. And again, there's a Fourier-Mukai transform, which takes the fluxes to these dualized fluxes. This is actually a bit complicated to write down because there's now lots of components that gets interchanged. And I'm not showing this here. So this is interesting because if I may bother you with this diagram here, because this can now be seen, as I will explain a little bit more on the following slide, and when we get to the M-algebra. This fully doubled spacetime is actually a small version, like the 10-dimensional version of the basic M-algebra. So down here, I'm showing the same fiber product that we just looked at, and I'm going to claim now that, just focus on the middle piece here, that there is another fiber product sitting over this double spacetime, whose tip is actually the M-algebra, and on the right we have the extended type 2A algebra. I'll come back to this diagram maybe in a moment. Let's skip ahead and just look at this M-algebra that I just claimed appears here. So maybe in small steps. So as you all know, maybe, but just to recall, so the M-algebra, or whatever it's called, the fully extended supersymmetry algebra in 11D, is a super Lie algebra, which is the maximal central extension, one way of thinking about it, of the superpoint that we just looked at. So since this has the co-frame on the superpoint consists of just the psi, which is a commuting spinor in the sense that it's a one-form valued spinor, a spinor valued one form. In any case, one can find that the only spin invariant two forms that one can build here are just those given by contraction with the gamma matrices, which means that with the Clifford elements, I should say, which means that the super algebra we're looking at is just generated by the psi's that we already looked at, the e's that we already know, and then there's 2 index e's and 3 index, 5 index generators whose differential just generalizes the previous differential of the E, where a differential of EA was just a single index gamma sandwiched in the psi's. The differential of the 2-index E is the corresponding 2-index Clifford generator sandwiched in the psi's, and similarly for the 5-index E. I'm choosing some peculiar signs here just to make the following relation, the following fierce decomposition nicely manifest. One can choose different signs than other signs pop up elsewhere. So with this M-algebra, which now has the ordinary super bracket and these central charges here, so these are the dual incarnations of what usually called the Z central charges of the supersymmetry algebra. One can transform it by just summing all the E's, all these generalized field-bound fields together, contracting them with gamma matrices as follows. So the 1-index guy we contract with the 1-index gamma matrix, the 2-index field-bound with the 2-index gamma matrix, and so forth. And then by fierce decomposition, one finds that this algebra, now this transformation, is equal to just this one, which looks almost trivial. So there's a closed psi, and it has this d alpha beta defined here, combining all the E's, whose differential is just psi alpha psi beta. So in this form, it's absolutely manifest that an automorphism of this DG algebra is given, the automorphism group is just GL32. It acts on these spinorial indices in the evident way, and it evidently preserves this differential. So this is the brain rotating symmetry, as originally pointed out by West and others way back. And that will maybe play some role in a moment. For the discussion of supertangent spaces now, it's useful, or at least suggestive, it's not necessary, but it really helps with understanding the structure here, to follow an old suggestion that maybe goes back to Hull in 1997, or maybe others. I guess Townsend had a hand in this. Anyway, it's a standard construction. Let's just to more clearly see what is going on, let's take the components of the bosonic body of the M-algebra, and just split off temporal components. And whenever we see a temporal component in one of these higher index forms, let's just write the corresponding Hodge-dual component, which is equivalent, but has the advantage that it has no further temporal component, and hence can again be interpreted as an actual charge for probing this space-time. So by just applying this yoga to our M-algebra, we see, well, the M-algebra itself, the bosonic piece, can be understood as having one copy of 11E spacetime, that's the dual to this E. Then it has one copy of the wedge product of its cotangent space, that's a copy of this 2-index thing, and similarly a wedge product of 5 of these cotangent bundles. And so doing the space-time split, we can think of this as being a time component, a time direction, space direction. There's M2 brane charges here, there's M5 brane charges, and there is in quotation marks corresponding 9 and 6 brane charges. And in this form, it's good to think of the reduction of this M-algebra to 10D in the usual fashion. And that turns out, of course, to be the fully extended type 2A algebra. And the thing I want to point out here, which is the reason why I'm doing this, is that in doing the analogous thing now for type 2A, we see that by just working out the components, we see that it actually starts out as this fully doubled space-time. So there's the 10D space-time component, but then it has a dual, which in the M-algebra appears as the well, I say this, sorry, maybe I'm getting ahead of myself here. It appears as a wrapped M2 brane modes. So from the point of view of 2A, we see a copy here of string charges, and then there's the D brane charges and S5 brane charges. But important to notice maybe is that the first two summons here, they are exactly what previously in the discussion of T-duality we identified as the fully doubled super space-time. So there's maps now. These are two of the maps in this big diagram that we looked at before, from the M-algebra to the 2A algebra to this fully doubled spacetime, which are the identity on the spinor, are the identity on the spatial E's, so E is smaller than 10 here, and identify the string charges in 2A, unsurprisingly, with the EA10, so with the wrapped, in a sense, membrane charges over the being wrapping over the M-theory circle. So this, to go back to my big diagram, this gives the first indication of how this double space-time, being sort of a reduction where you forget the further brane charges of the fully extended 2A space-time, is in turn not unlike the M-algebra. And now we come finally to the observation that then leads us over to exceptional geometry. Now we see that there's one more nice aspect of this M-algebra. If we take its spatial component, the R10 here. So if we drop the time component for a moment and just look at the spatial part, and then in addition restrict that to some n-dimensional subspace for small enough n, then the resulting algebra is just, or the resulting tangent space is just the traditional exceptional tangent space that's usually attributed to Hull's article in 2007, where up here, you see, this was the main brane charges, the 5 brane charges, the 6 and the 9 brane charges in quotation mark, which do not actually appear, the last one, in these low dimensions. We can just count the dimensions and see if we were to regard this M-algebra now as our tangent space model for whatever it is, a tangent space model of, we can just count dimensions and see that the dimensions are just those of the basic representations, the fundamental representations of the corresponding U-duality Lie algebras that one expects in these dimensions, the E-series algebras indicated on the right here. So this is a classical observation, but it's also classical and was maybe somewhat puzzling that this suggestive pattern actually breaks here. So people, many in the audience have been involved in various ways to variants of this construction, but certainly the original article by Hull, for instance, stopped at this point, and something does change in that if one were to go higher here to n equals 8 and higher, then one sees that the corresponding dimensions that one gets by counting up how much there is in the M-algebra, it's just not enough to make a representation of the corresponding next En algebras. This happens already for E8, even though this has finite dimensional wraps, but the next one, its basic wrap is just not captured by this M-algebra here. And it breaks even more, of course, for the higher ENs where we would need an infinite dimensional wrap, which cannot be given by this finite dimensional space. But still, and that was our original question, the identification of the M-algebra as an M-theoretic incarnation of this fully doubled superspace time that I tried to indicate from this tangent space-wise T-duality suggests that there's something going on, and the M-algebra should in some sense be a super exceptional tangent space after all. And that was the observation we made, which I think is the reason why I'm invited to speak here, that we observed that the pattern does complete exactly if only we observe that we shouldn't be asking for representations of the En algebras themselves, but we should be asking for representations of their involutory subalgebras, their maximal compact algebras. And I guess I'm carrying owls to Athens now in saying this, but let me say it anyway. So as people in the audience have been majorly involved in, there's 2 observations here to be highlighted, which I'm going to use to motivate or explain how this pattern should actually be completed. And this is the aspect of local hidden supersymmetry and of spinorial hidden supersymmetry, as I'm calling it now. So as you know better than me, actually, these En algebras, these Kac-Moody algebras are actually supposed to play the role of global symmetries, of global U-duality symmetries of compactified supergravity, whereas what we really have a right to expect to act on supertangent spaces are local symmetries, just like in the ordinary case where the Lorentz group is a local symmetry of supergravity, and that's what actually acts on our tangent space. And the other observation is that these these local symmetry involutory subalgebras, they actually have finite dimensional non-trivial wraps. In particular, they have a spinorial representation, which looks just like the 32, that is the Marjorana representation of our SO1,10 group. And using these observations, one sees that this table completes as I'm indicating here. So I'm getting these dimensions still by just unwinding my bosonic body of the M-algebra, which dimension it has as we restrict it appropriately. And we find that now in dimension 8, what we actually get is a total dimension of 120, which happens to be, it's not the fundamental rep of E8, but it is the fundamental rep of SO16 and so forth. And the way this actually came about, this is why at some point I started bombarding some of the members of the audience with emails, is I was sitting there and thought, well, how can I prove, or how can I show that there's some completion to this table? And then I thought, well, I do know what I'm looking for. I can just count these dimensions. I just take my M-algebra and count these numbers up, so I know what representation I need to find. And so I ended up, silly as this may sound, to just Googling for, in quotation marks, for these numbers, putting them in quotation marks to force Google to really find that number, and for the corresponding name of the EN algebra. And it's that how I think first Benedikt Koenig's article showed up, where just very recently it's shown that there is a rep of the maximal compact involutory subalgebra of E9, which is sort of the lowest dimensional non-trivial rep. It appears in some expansion of on a higher parabolic levels, and it has exactly the required dimension 256 that we would need to have in order to complete the pattern here. And then proceeding in this manner and bombarding you with emails, it turns out that indeed all these reps exist in exactly the dimensions that one would hope them to exist for this pattern to make sense, and they're related under the correct restriction maps. So if my attempt of kind of summing this up is this little diagram where we see that as we go to the full M-algebra, where we also include the time direction, so that the maximal compact subalgebra we're going to use is actually, as was kindly pointed out to me, is the temporal version. It's not actually a compact subalgebra, it's the temporal involutory subalgebra, which I'm denoting K110 here. It goes in the literature under different names, H11 or some other names. That kind of appears to us now in different guises. On the one hand, it's the bosonic body of the M-algebra, the way we originally thought of it, being this decomposed rep of spin 1,10. But it's also actually the sort of the fundamental representation of this temporal or hyperbolic involutory subalgebra K1,10 of E11. And it's also a rep of K10 and so forth. And so we see that there's these different perspectives here on the N-algebra, where even though we started out it being just something that looks like just ordinary space-time extension, actually very naturally now is seen to be part of this pattern, or at least of an aspect of this pattern of exceptional geometries. And of course, since this is an infinite dimensional Lie algebra, its action on this finite dimensional space has to factor through a finite dimensional Lie algebra. And that turns out, as is also shown by members of the audience, that turns out to be nothing but the SL32 rain rotating symmetry that we already saw is an automorphism of the M-algebra. So the point here is to amplify that even though these statements that I'm showing here have all been discussed in the literature for what I now identify as the bosonic body of the M-algebra, but at this point, we immediately see that this actually all lifts to automorphisms of the M-algebra as an actual super Lie group. So this is actually a symmetry of the super exceptional tangent space, if you will. So that is the main observation, which kind of justifies or seems to justify thinking of the M-algebra as in some way, well, in this way, completing the previously truncated hierarchy of exceptional tangent spaces and at the same time lifting them to supergeometry. And So that's the main observation that I'll have to present here, but I do want to maybe close by making some comments now on further implications or further steps, further observations one can make here. So this is a little silly computation of mine, which I'm showing here to amplify that we should now maybe ask, given the way I've motivated it, what is it now? What now about realizing, for instance, T-duality on the M-algebra, right? So the motivation here was that we wanted to say we have a very good understanding of T-duality on this double space-time, and we would like to know how to lift this from 10D to 11D, going just on the level of tangent, supertangent spaces, understanding that these are kind of the avatars of the full theory in a sense. So this makes us ask now if we can find some analog of this Poincare form, which recall was the thing that absolutely controlled T-duality down here. Is there an analog of this on the M-algebra? As you can see, I'm already indicating it here. There is actually. But before we say that, maybe it's useful to observe that does not seem to be an actual, this is maybe, I don't know, maybe a trivial side remark to you, but given that we have some exceptional symmetries now acting on our M-algebra, that we know now that we should think of this SL32 automorphism of the M-algebra as encoding some kind of duality symmetries, we might first want to ask if T-duality is implemented by an element of SL32, but I don't think it's quite. So one can see that the SL32 generations, operations that are generated by exponentiating gamma 10, say, they do mix the ordinary space-time coordinates with their T-duals in this form here, and mix the NS5 branes accordingly, the NS5 brane charges accordingly, as one would expect for T-duality, but they just mix them, they never swap them. So there is some kind of T-duality frame change here, but an actual T-duality operation where we just want to just swap these is not actually part of the SL32 symmetry, I think. And that's fine. Actually, the way I've motivated or I described it, we already know that T-duality actually wants to be implemented as a kind of Fourier-Mukai transformation on these doubled and hence exceptionalized spacetimes. So one thing we can ask is there now a lift of this Poincare 2 form from the doubled spacetime to the M-algebra? And so to the M-algebra as such, there is not, but one can observe now that our motivation, our explanation of the role of the M-algebra as being an exceptional tangent space was all based on looking at just the bosonic components here. So what we can actually do without changing this argument in any way is we can look at for fermionic further extensions of the M-algebra. So what we can do is we can throw in further fermionic generators, another spinner, and ask if that is maybe sufficient in order to lift our P2. And that turns out to be the case. There is a fermionic extension, which is actually a very special case, or one of the special cases of the whole one-parameter family of so-called hidden extensions that Daria and Frey had originally given. There exists an element, after we do this fermionic extension, there is a three-form, a super-invariant three-form, P3, whose differential actually trivializes G4, the pullback to of G4 to the M-theory spacetime. Its fiber integration down to the 2A algebra is a hatted Poincare form, which still trivializes H3A. And we can now see the interesting effect that this is a combination, turns out, of the P2 that we're actually looking for. Remember that the 2A algebra is like the doubled spacetime, but with sort of more brane charges thrown in, where we think of the doubling as being that coming from the string charges. And so turns out forgetting the brane charges in Whitehead P2 is precisely our Poincare 2 form. So this is a way in which the Poincare form lifts, and we don't know yet at this point what exactly that now entails for how we would like to formalize T-duality or an M-theoretic lift of T-duality, but it shows that we have some good candidate space here that carries the correct lift of the structure that fully controls T-duality down in 10D. I have a side remark here, which maybe I'll skip over, unless maybe we can come back to this if there's any questions. I suppose I have like maybe 15 minutes left or so, or 10. Let me come to, if I may, to the outlook that concerns me personally most about this, and which has to do with the flux quantization that was originally part of the title of my announcement, which I then changed by request from the audience. But allow me to mention it because I think it's important if we think, as we should probably, about actually going towards identifying some aspects of M theory here. So for just a second, I'll speak about something that looks different, but I'll come back to what this has to do with my original motivation of supergravity in just a moment. So it's an underappreciated fact, I would claim, arguable, that it's unappreciated that a C-field configuration in supergravity is actually more than just a differential 3 form, and also more than even if you're sophisticated and think, well, okay, let's throw in the dual 6 form. It's actually more than that too. Namely, this is the data, like if we're really speaking about forms, this is the data that applies or that defines the C-field on a single chart of our space-time. But if our space-time is not just Minkowskian, if it has non-trivial topology, then a global C-field configuration must involve more. It must be gauge potentials C3 and C6 on a chart, on each chart of an open cover of space-time. But then there must be some kind of gauge transformations on double intersection of these charts that tells us how one of this set of local data is related to the other. But since these are higher forms, they will have gauge of gauge transformations, which we will have to specify on triple intersections of charts and so on. Until we come to a top dimension, top degree of intersections, we will have to impose some condition on what these gauge transformations have to satisfy, which a condition that will correspond to imposing a quantization law on the, on the fluxes and hence on the charges that the M-brane charges that source them. Since if this sounds abstract, let me just recall that this is standard and well known for electromagnetism, where, ever since Dirac, since the 1930s, we know electromagnetism is more than what Maxwell thought it was since 1850. It's not just given by gauge potentials, AI, that are globally defined one forms. No, it's these AIs on each chart of an open cover. And then on double intersections, they must be related by gauge transformations, R-valued functions that tell us how these choices of local gauge potentials are related. And then importantly, on triple intersections, these gauge transformations themselves must satisfy a condition, namely their signed sum has to be an integer. This is equivalently, this is the Czech data of what makes the electromagnetic field be, the way it's usually formulated these days, be a connection on a principal circle bundle, principal U1 bundle. So, as well known now, this was Dirac's original observation in a sense. It was, some hindsight that imposing this flux quantization condition is what stabilizes the solitons of electromagnetism. Well, usually quoted are the Dirac monopoles, which remain hypothetical, but it's maybe fun to notice that what's called Abrikosov vortices in type 2 superconductors, the fact that they appear in integer numbers is just the same flux quantization mechanism that makes the Dirac monopoles have quantized charges, and the Abrikosov vortices are actually observed. They're an experimental fact, which is good to know. So this stuff here, this is not just hypothetical. This is known to be important, and hence, if it's important here, we expect that it's important elsewhere. Just to highlight that the conjecture, often stated conjecture, that the RR field is somehow the RR fields and hence the D-brane charges are in K theory, as people say, is just another version of this flux quantization condition. Then one observes that this duality symmetric Bianchi identity, and now you see we're coming back to the original discussion of these superfluxes. The duality symmetric Bianchi identity is satisfied by the RR fluxes happens to be exactly the relation that is enforced by the image of the Chern character from K theory. So if you have a K theory class and you compute what's called its Chern character, it's given by a bunch of forms that satisfy exactly this relation. That's what characterizes the Chern character of K theory. And this is really, if one goes to the bottom of it, this is what, even though it wasn't always stated quite this concise form maybe, but this is really what motivates the original conjecture that maybe the R fluxes are flux quantized in the analogous way here in K-theory because they're character images of this form. So it does make sense to ask that the full globally defined R fluxes are not just given by the Fs and also not just by their gauge potentials, but actually by a co-cycle in differential K-theory. And so it seems clear that one should ask the analogous question actually for the C field in 11-dimensional supergravity. And so one is actually faced with a question there, what, if any, is there a cohomology theory which some kind of character image is defined, whose elements are forms that are precisely of this duality symmetric form that we saw characterizes the Bianchi identities of the C field flux. And there is such a cohomology theory. Well, there are many of them. There's sort of a canonical one called Faux cohomotopy. And why I'm highlighting this here is that, as in the K-theory case, some people, like I think Dan Fried, have tried to think a lot about how to deal with the fact that when people make this K-theory conjecture, they kind of conveniently forget about the duality constraint that is supposed to be there, in that the Fs are meant to be Hodge duals of the higher or lower dimensional Fs, right? F2k has to be equal to the Hodge dual of F10 minus 2k. And it may seem, depending on how you approach this, may seem that you've forgotten this equation of motion, if you will, just looked at the duality symmetric part. And the question arises then whether it's actually okay to flux quantize, say, this in K-theory, given that one of the constraints was actually neglected in looking at these characteristic equations. The same question can be asked here if we just kind of flux quantize as controlled by these duality symmetric Bianchi identities. Did we neglect the crucial, the dynamical, if you will, Hodge duality constraint? Well, but no, we just saw that if we're actually on superspace, then the equations of this form, now imposed on the superflux densities, are actually the full equations of motion. And the star is implied, which shows that it's actually complete to just flux quantize this. This is one of the important impacts, I think, of the superspace, the duality symmetric superspace formulation, that everything involving the metric, the Einstein equations, and also the Hodge duality relation is actually implied by sort of just this, if you will, cohomological condition, which doesn't look metric. It's a cohomological condition, but imposing it on superspace by the magic of superspace implies all the metric structure that we expect to see. Similar story is for the holds for the M5 plane that I mentioned at the very beginning. Here too, it's remarkable that imposing the Bianchi identity, the sort of twisted Bianchi identity for the H3 flux on the 5-plane world volume actually implies that this H3 is not just that it's self-dual, but it actually satisfies which some people seem to have forgotten these days, that in the large field limit, if you're not going to tiny values of H3 is not actually self-dual. Some people call it's non-linear self-dual, but it satisfies a very complicated different condition. It's determined by its self-dual part. But anyway, the full condition on H3 that should be there for the M5 plane is again actually implied by this very simple looking Bianchi identity on superspace, which of course becomes very complicated by expanding it in the supercomponents, the superfield components, which is how this magic works. In any case, in summary, this means that on superspace, the Bianchi identities on the superfluxes determine the admissible flux quantization laws, and hence determine ultimately the possible global completions of the supergravity field content. This makes a real choice, like which completion you choose, makes a real difference, which cohomology theory you choose in order to define the global nature of your field. So there's an actual physical datum that needs to be provided in order to complete supergravity globally. And so I think it's interesting, and that shall be the last thing I'll say here before we maybe go to questions. It seems interesting to me that there is two sort of known ways of going about actually completing 11-dimensional supergravity, and they come together in super exceptional geometry. Namely, on the one hand, the global completion of 11-dimensional supergravity fields, the flux quantization, is controlled remarkably by supergeometry, by the superspace formulation of supergravity and of the super 5 planes and so forth. Whereas, for lack of a better word, I'm calling the E10, 11 program here, seems to indicate that there's something like a local, if you will, completion of 11-dimensional supergravity. It looks much larger in some sense. It has all these infinite dimensional Lie groups, but still it's concerned with forms or field content that are of the local nature, not globally. And so this is controlled, as we now know, by exceptional geometry. So this suggests that the full completion of 11-dimensional supergravity should at least combine these two and maybe more. And it seems quite suggestive from this point of view that some super exceptional geometry is needed. And that's why it might be worthwhile to look at formulations of supergravity on 528-dimensional superspacetimes that are locally modeled on the M-algebra, given that now we know that the M-algebra in some precise sense is a good first order, maybe approximation to exceptional geometry. So that's what I would have to say for now. And maybe I'll stop here and we check if there's questions.
Yeah, thank you very much, Urs, for the nice talk. Questions from the audience?
I have a
Manji.
question. At some point, you mentioned a fermionic extension of the M-algebra.
Yes.
Does it mean the M-algebra has 32 supercharges? And that means you add another supercharge, or what does it mean?
That's right, yes. So it means, yeah, I don't have the formula on these slides here, but it means that if we look at the Chevalley-Eilenberg algebra of the M-algebra, we add one more spinorial object, phi, which is again a one form valued in 32. And we declare that d of phi is, and what is it? It's essentially all possible ways of contracting a gamma with an E and a psi. So it looks like d of phi is gamma A acting on psi times EA, and then do the same thing with the higher index E's and the higher index
But
gammas.
just let me try to understand. I mean, if I have a Q alpha for the 32 supercharges, so you
Yes.
add another, call it S alpha,
Yes.
two components,
Yes.
and you I'm not quite sure how this doubling comes about, because it's again combining 2A with 2B supercharges. Is this what underlies this?
When you say doubling now, are you talking about in the sense of doubled space-time?
Well, you have double space-time, and then maybe you also need to double the supercharges.
Oh yeah, right. Yeah, that's true. I see what you mean. Yeah, well, yeah, that's true.
Okay.
Yeah, that's true. Yeah. So in the what I call here the hidden M-algebra, which is what Daria and Frey originally defined long ago. Yes, there are these EAs which now, at least the EA, EA2, the EA10 components can understand as being actually doubled space-time directions. Yes, they get accompanied by another fermion. That's true, yes.
Okay. But it would be good if you at some point could write out this full algebra involving now 64 supercharges.
Oh yeah, absolutely. It's just not on these slides. So we discussed this in much detail in this recent article, the hidden M group. We write it down in much detail. I could write it down for you now. I'm bad at. I actually
don't
have the
worry,
program.
I can look it up. Okay.
Yeah.
Thank you.
Yeah, more questions. If there is none, I have another one, perhaps. Just very general, because you mentioned before the talk even started that there was a gap with the rheonomic approach in this business, and I didn't quite understand what it is. Is it forgetting this Hodge duality condition in the flux quantization, or is this something else?
Yeah. Yeah, we can speak frankly here, maybe. So there is first of all.
Actually, I can also stop recording if you want. So, so yeah.
Yeah.